Hello everyone! Today I'll be presenting our work on enhancing self-supervised learning for Earth observation using a dynamic dataset pruning strategy. We've applied this method to create Ocean SAR-1, a new foundation model for ocean observation using Synthetic Aperture Radar or SAR imagery. So as you all know, self-supervised learning is revolutionizing Earth observation. It allows us to train powerful foundation models on vast amounts of unlabeled satellite images. These models then show strong performance across many different tasks. And generally, bigger models and bigger datasets mean better performance. However, Earth observation data present a unique challenge, especially compared to natural imagery like ImageNet. And this challenge is their extreme redundancy. For example, over land, you will mostly see endless stretches of forests, deserts, or clouds if you take an image at random. Similarly, over the ocean, you're mostly going to see waves, more clouds, or sea ice if you're at high latitudes. So, simply using all the available data naively to train a model isn't efficient and can lead to biased models. Many existing Earth observation foundation models use pre-curated datasets, like functional map of the world, for instance. And these datasets are often balanced using metadata, like land cover. However, such curated datasets don't exist for all types of remote sensing data, like the Sentinel-1 SAR data that we use in this study. And creating such curated datasets requires a lot of work, and it can be very difficult, especially if metadata is sparse or uninformative. And this is the gap that we address in this study. What we do is we introduce a dynamic dataset pruning strategy, a method that intelligently refines the training dataset during the self-supervised learning process. A key advantage of it is that it doesn't require a pre-existing feature extractor to decide what data to keep, and it makes it ideal for new domains or sensor types because the training methods becomes completely self-supervised. So we've applied this method to a challenging dataset, as I mentioned earlier, Sentinel-1 wave mode SAR imagery, of which you can see a few examples here. Over the oceans. We focus on the oceans. This is a large data set. There's about 12 million 20 by 20 kilometer images that have been taken since 2014, the beginning of the Sentinel-1 mission. And as I mentioned, these images are highly redundant, as you can see here. Many images will show waves, rain cells, or sea ice and be very similar to one another. We used the Dino pre-training framework in this study, but our method integrates with any self-supervised learning framework, really. And here's how it works. So first, we start by training the model for a few epochs on the entire dataset. And then, periodically, every few epochs, we're going to prune the dataset. And how this pruning works is with two steps. The first step is clustering. So we take the image features from the current version of the model, the image embeddings, and we use them to identify clusters of similar images across the dataset. Then we're going to sample the dataset. We sample an equal number of data points from each of the clusters. And this ensures that our training subset remains diverse and balanced in the embedding space. To make this computationally efficient, we define cluster centers using only a fraction of the dataset, not the whole 12 million images, typically just 10%. Initially, we sample images close to the cluster centers, and as training progresses, we gradually allow the sampling to sample images further and further away from the cluster centers to expose the model to more varied data over time. We evaluated our approach using three distinct downstream tasks focused on the ocean. The first is the classification of geophysical phenomena using the 10GOP dataset. So these are phenomena like classifying an image as containing sea ice or icebergs or an atmospheric front or rain cells, for instance. The second is a regression task, the estimation of the significant wave height using data which we annotated for the purpose of this study with wave height data from satellite altimeters. And the last one is also a regression task, the estimation of wind speed at the surface using ERA5 reanalysis data co-located with Sentinel-1 SAR imagery. We also experimented with different pruning levels, for instance, retaining only 50 or 25% of the datasets at each pruning step. Our results are really compelling. Dynamic pruning leads to an overall increase in performance on all of the downstream tasks. For instance, we saw a significant 2.5 to 3% improvement in accuracy for the 10GOP classification task. Importantly, this performance gain comes with improved computational efficiency. So you see here that the model converges faster when it's trained on a pruned dataset. And this is likely because regularly resampling from a redundant dataset acts as a form of regularization, helping to prevent overfitting and guiding the model to learn more robust features. So we've named our specialized foundation model OceanSAR-1, and when we compared it to existing SAR foundation models, in both zero-shot and fine-tuning conditions, it consistently outperformed them on our 3 ocean-specific tasks. The improvement was particularly large for the wave height and wind speed estimation tasks, which are more difficult than the 10GOP classification task. So this isn't entirely surprising, the fact that our specialized model performs better than existing SAR foundation models. And indeed, most of these existing models were trained on a different type of SAR data, which is ground range detected, or GRD, imagery and exclusively over land, while our model was trained exclusively on Sentinel-1 single-look images over the ocean, which makes it highly specialized. So, to summarize our contributions, first, we've introduced an effective dynamic pruning methodology for self-supervised training on highly redundant Earth observation datasets, which boosts both efficiency and feature quality and offers a fully self-supervised training strategy on any kind of remote sensing imagery. Second, we trained a specialized model for ocean SAR imagery, and we are releasing the weights for OceanSAR-1. This is the first in a planned family of models dedicated to ocean observation from SAR imagery. And third, our work highlights that for specialized satellite modalities like Sentinel-1 wave mode over the ocean, a focused unimodal model can actually outperform larger multimodal models, especially when combined with smart data curation like our pruning strategy. So as I said earlier, this approach offers a scalable solution for dataset curation in Earth observation, which paves the way for more efficient and generalizable foundation models. So thanks for your attention. I'm happy to discuss this further. Feel free to contact me, and I hope you found our poster interesting. Thank you.